Good evening, everyone, and welcome to this lecture, Photoelectric Effect, Lecture 3. We are dealing with the last class. I think we dealt with the number of photons and energy and intensity of the photon. Yes or no? And we had seen how we can find out the intensity of this photon. Yes or no?
Yes, sir.
Okay, I think we had
Yes, sir.
discussed the problem as well. The problem of the bulb, how much photon that bulb emits. Yes or no? Just have to divide the power by HF. Yes or no?
Yes, sir.
Okay. In today's class, I have seen something, so I will start with that, and we will write the heading that fashion as well. This is force exerted by light on a surface. So we'll write the heading force exerted by light on a surface. Force exerted on a surface when light or any radiation falls on it, it exerts force. So I will do it in two different cases. In first case, it falls on a perfectly reflecting surface. It falls on a perfectly reflecting surface. So you understand the meaning of a perfectly reflecting surface. It is going to reflect everything. We understand this? Now this is a small diagram that you can draw if you want to. This is the small diagram that we can draw, and we will just write what is happening here. Picture is a bit black. I hope you like this color. It's never come on the class, in the class. I hope you like this color. So you can see what is happening here, my dear friends. Since it's a black color, I will have to use a lighter color. You can see there is a photon which is incident on it. Photons are incident on it. They attack it, fall on it, and then they are moving back, and their momentum is reversed. Yes or no? So what you have to remember when you are dealing with this question, first you have to understand that what all things are given to you. So n number of photons are falling. Capital N is the number of photons that are falling, or sometimes they will give you small n. This is the number of photons falling per second. So this question can be given in terms of capital N, which is the total number of photons, or it can be given in terms of small n, which is the number of photons falling per second. Now, without getting much into the details of it, because we don't require it anyways, I'll tell you what all things they can ask you. They can ask you what is the change in momentum of one photon. Only one photon, if you see what is the change in momentum, that will be equal to 2h by lambda. Do you understand this? Yes or no? Change in momentum of one photon. Total change in momentum is 2nh by lambda. I multiplied by the total number of photons. Change in momentum by time, that becomes my force. So this is the force, 2nh by t into lambda, that becomes my force. This n by t, capital N by t, becomes my small n. So it becomes 2 times small n h by lambda. This is the first formula of force. The force on the surface can be written in this form, or it can be written in this form. Capital N by t means total photons divided by total time. Small n means number of photons falling per second. Do we understand this? We can also write this force as 2 times P by C, We have already seen the formula of P. We put that formula of P and we can get this formula for force. So you just have to remember this formula for force. Can you remember this? This one and the yellow one. They might also ask you what is the pressure. So pressure PR is force divided by area. To divide this equation by area, power divided by area is intensity. So the answer for pressure becomes 2I by C. If you can remember these questions, these formulae, it might come in your exam if your exam paper they make a bit tough. I'll give you 2 minutes to note this down. Everyone can see me, everyone can hear me because all of you have disappeared all of a sudden.
Sir,
Yes, beta?
sir, am I audible?
Yes, you are audible. Can you see, can you understand what I've written here?
Yes, sir.
Okay. Note it down, please.
Done, sir.
Boys in the class, are we done, bacha? Yes, beta? Can't hear you.
Completed, sir.
Completed, sir. Okay. Now, this was the case of a perfectly reflecting surface. Now, can you tell me what could be our next case? The first case was the case of a perfectly reflecting surface. What could be our next case? Yes, my dear friends. What would be our next case?
Perfectly absorbing surface.
Yes, the next case is definitely perfectly absorbing surface. So in this case, what is going to happen here, bacha? The photons after falling are not going to go anywhere, but they are going to get absorbed. Now, if you can understand and remember the previous formula, you should be able to tell me the formula in this case. What will be the formula of force in this case? The formula for force in the previous case was, and I will not tell you because you will have to remember it. What will be the formula of force in this case?
P by C.
P by C, that is correct. That is one way of saying it. Or you can say it also in the other way, N, small n, H by lambda. Or you can call it as P by C. Intensity in this case will be, sorry, not intensity. The pressure in this case would be I by C. Do we understand this?
Yes, sir.
Okay, I'll give you a minute to note this down.
Done, sir.
Everyone?
Sir, not sir.
Let me know, bacha, once you're done. Have you noted it down, bacha?
Completed, sir.
Everyone, sir?
Yes, sir.
Okay. Then comes the next case. If it is if it is incident at an angle and it is perfectly reflecting, let me take this perfectly reflecting. So let us say that it falls at an angle theta, and this is perfectly reflecting surface. Then what will be the force? Perfectly reflecting at an angle. If you understand perfectly reflecting at an angle, you should be able to tell me what will be the answer for perfectly absorbing at the same angle. Yes, bacha. Anyone with an answer? Well, let us not waste much time into it. So the force in this case, yes,
2 I by C cos theta, sir.
yes, force is 2p by c cos theta. Well done. And pressure is 2I by c cos theta. Now you can also write if it is perfectly absorbing, then the answer would be F will be P by C cos theta. Pressure would be I by C cos theta. Do we understand this?
Yes, sir.
I'll give you a minute to note it down.
Completed, sir.
Boys, have you done?
Sir, wait, sir.
Wait, sir. Okay, sir. Let me know once you're done, bacha. Shall we move ahead?
Completed, sir. Completed.
Okay. So this was perfectly absorbing, perfectly reflecting. Let me see. Okay. Let us move ahead. I think we are good with this. And let us move ahead into the main concept of this chapter. The heading of this chapter was photoelectric effect. And we still have not started photoelectric effects. So welcome to the heading of this chapter, and we now officially start. So now we have the entire tools to start something known as the photoelectric effect. Now, what do you understand by this photoelectric effect? Anyone? When I say the word photoelectric effect, what do you understand by this? Do you have any idea about photoelectric effect? Remember, in physics, most of the names of processes, if they are not named after a scientist, whatever they mean, it's very evident in the name itself. Same is the case with this gentleman as well. Can anyone tell me, what do you mean? What do you understand by photoelectric effect? Yes. What do you mean, or what do we understand by photoelectric effect? Yes, bacha. So something related to light and electrons. What something? Something at this stage is not the correct thing. Can you explain further on that something? Something what something?
Sir,
Something, yes. What something?
circuit.
Sorry, bacha.
Current passes through circuit.
Current passes through a circuit. Okay, that adds something to what Abhiram was saying. Anything with a more insight or would like to add something more here? It has got something to do with this, something to do with light, something to do with electrons, but what exactly? Photoelectric effect. Look at the definition. Look at what it is saying. Photoelectric effect. So photo means light. Electric means electrons. So something will happen with light and electrons. What will happen with light and electrons? Yes, Abhiram, that is correct that you are thinking. Now, whenever light of sufficient energy, forget about light. Now, you must be having your chemistry lessons and you must understand that everything is made up of atoms, electrons, neutrons, and so on. Yes or no? So, everything is made up of atoms and electrons and neutrons. Now, when we go higher up in the periodic table, what we see is the electron which are in the outermost shell. They are the most loosely bound electrons. Yes or no? Now, if we can give these electrons sufficient energy by some means, they can actually become free from the bondage of this nucleus, this atom, and they can wander freely inside the metal. Yes or no? So you have to impart it some energy in some form. Now the question is, how can you give these electrons that much of energy? Well, we now know that light has energy. Light has photons, it has energy. If you allow light to fall on a surface, and if this light has sufficient energy, this energy falling on this surface of a metal can emit electrons. This effect is known as photoelectric effect. So I can accomplish this removal of electrons from the outermost shell by throwing light. Can you think of something else? If I can heat up the metal sufficiently, the electrons in the outermost shell can get enough energy, they can roam around here and there. That is known as thermionic emission. If I can place this metal field in a strong electric field can accelerate the electrons, can give sufficient energy to the electrons, they can become free and they can say bye-bye to the atom and okay, I'm going, bye-bye atom. So it can be done by a electric field. Or what we can do is, this is a metal surface, I can bombard it with particles. These particles can be electrons, these particles can be protons, this particle can be neutrons. I can bombard them with these particles. If these particles collide with these electrons can just go away from that metal surface. In all these cases, you will have electrons emitted from that surface. These are different types of processes. What we are going to do here is we are going to emit these electrons by making light to fall onto it, and that phenomena is known as the photoelectric effect. Do we understand this? Is it clear to everyone? When light of sufficient energy falls on a metal surface, electrons can be emitted. This phenomena is known as photoelectric effect. The electrons which are emitted are known as photoelectrons, and the current which is established is known as photoelectric current. Do we understand this? Yes or no, everyone?
Yes, sir.
You can just note it down in your language. Remember, the language is not important. What is important is that to understand the phenomena, and the phenomena is very simple. When light or electromagnetic radiations of suitable wavelength. Now, what do I mean by this wavelength? Instead of this wavelength, you can write sufficient frequency, or you can also write sufficient energy. Energy is the term that you are more concerned. These photons or these radiations must have sufficient energy that they are able to liberate these electrons. If they don't have this sufficient energy, nothing will happen. So when electromagnetic radiations of sufficient energy, or you can call sufficient wavelength or suitable frequency, when it falls on a metal surface, electrons may be emitted. This phenomena is known as dear photoelectric effect. The electrons which are emitted are known as photoelectrons, and the current which is established is known as photoelectric current. So this is a very simple description of what is happening. You can see this gentleman. These are electromagnetic radiations. They are falling on this. This is a metal surface. I hope you can see this vertical plate. It falls, and these gentlemen are electrons which are emitted. And they are getting to this side, and we have a current established in the wire. Do we understand this? Yes or no? It is going above what it's saying bye-bye. I'm going. Don't worry about me. Okay, I'll give you 1 minute to note this down. Remember, you have to draw the diagram. Diagram is the only thing that is important in this chapter. Have you noted it down, bacha?
Completed, sir.
Boys have completed this time. Girls are sleeping, it seems.
Completed, sir.
Completed. Well done. Remember, in this entire chapter, what we have to understand is a simple diagram and simple graphs. If we can understand those two things, we are done. This is all about understanding simple definitions and simple things. Now, the most important thing that we have seen or we should understand in this this discussion is when electromagnetic wavelength or when electromagnetic radiation of suitable wavelength, suitable energy, suitable frequency. What do you mean by this suitable energy or suitable frequency or suitable wavelength? What do you understand by this? Anyone can give any insight? Why we need suitable? Why can't any frequency? Le dum. I throw this light down and the electrons won't be emitted. Why only suitable frequency? Why only suitable wavelength? Yes. What is the reason? There must be a suitable. Why suitable? Everything is suitable. Light is light. This light or yellow light or this light, blue light. What difference does it make? Huh? What difference does it make? No difference. All is light. Why do we need suitable? Comes the next character in this movie, and that character is known as work function, denoted by W or sometimes W naught or sometimes phi. Any idea what is this W or W naught or phi? Yes, bacha? W or W naught or phi, what is this? Huh?
Sir,
Yes,
so minimum energy required to remove electron from a metal.
that's correct. See, these electrons are attracted to this central nucleus. They are not free. That this light will fall. They say, okay, light has fallen. Let's go now. They are not free. They are attracted to the nucleus. They are bound to the nucleus with some energy. Now, if you want to remove these electrons from their orbits, you must give it some energy, sufficient energy. You must give it some minimum energy. That minimum energy which is required to remove electrons from the metal surface is known as your work function. Minimum energy required to remove electrons from a metal surface. Now, those metals which will have a lower work function would be good for this photoelectric effect because they will require less energy. We always look for less energies. Whatever comes in less energy or less money, that is what is good, right? Whatever is costly or requires more energy, yeah, no one is worried about it. So we want metals which have very less work function. So this is the minimum energy required to remove an electron from the metal surface. Work function. Now we talked about minimum energy. So this minimum energy is this work function. We also talked about a suitable wavelength. Comes the next heading. What would be the next heading? Threshold frequency. Threshold frequency. What do you understand by this threshold frequency? This is normally denoted by the letter F naught. Yes. Huh? Any idea what is the threshold frequency? If you understand one thing, the other things should come on their own. Yes, bacha. Yes, Abhiram. It is the minimum frequency. Remember, light is falling on this metal surface. We need light of minimum energy. Now, this energy of light is coming from the frequency E is equal to HF naught. Therefore, this is the minimum frequency of falling radiations. This is the minimum frequency of falling radiations required to emit electrons. What is the minimum frequency you require? Then you can relate this work function with the threshold frequency. What will be the threshold frequency? What will be the relation between work function and threshold frequency? Anyone? Work function W or phi will be equal to H multiplied by F naught. This is the first formula that you must remember in this particular chapter. If the frequency of radiations falling, if the frequency of falling radiations is less than F naught, this will imply there will be no photoelectric effect. No matter how much light is falling. Do we understand this? Huh?
Yes, sir.
No matter how much light is falling, if the frequency of that radiation is less than this threshold, nothing will happen. I may allow a lot of light to fall. Hey, more light, more light, more light means more energy. No, more light does not mean more energy. More light basically means that more photons are falling. And we'll have to understand this. I see more light, that means more photons are falling. You understand this? Okay. So that I can write the same thing in a different way. For photoelectric effect to happen, frequency of the radiation must be greater than F naught. Just remember these small things. And these small things is going to make a hell lot of a difference in the final exam. Now we have talked about threshold frequency. Remember the definition that we wrote suitable wavelength, suitable energy, suitable frequency. What is the next thing that you have to understand? What is the next thing that we have to understand? We have seen work function. We have seen threshold frequency. What is the third thing that you have to understand? Yes. Huh?
Threshold wavelength.
Threshold wavelength. Yes, that is correct. Threshold wavelength. Lambda naught. What would be threshold wavelength then? I have told you minimum energy, work function, and all those things. I can expect that you can tell me this. Jeff. Minimum wavelength. No, Abhiram, it is definitely not minimum wavelength.
Maximum.
Maximum, yes. If the wavelength is, if the frequency is minimum, wavelength has to be maximum. Maximum wavelength. Of falling radiations to emit electrons from a metal surface. You understand this? Then we have this wonderful relation between W, which is phi, which is H into F naught. I can now write it as H into C by lambda naught. Yes or no?
Yes, sir.
Yes, sir.
Now, if I put the value of H, which is Planck's constant, C and lambda in SI units, I will get this energy, this work function in SI unit. But you must understand that SI unit joules is very big. This work function is very small. So we must use smaller units. And I told you one smaller unit that we'll be using in this chapter always. What is that smaller unit? Which one? Electron volts. And whenever you see H and C in the numerator, well, we know this shortcut then, that work function in electron volts will become 12,375 divided by Armstrong wavelength in Armstrong unit. Do we understand this? I gave you that shortcut for that.
Yes, sir.
Or you may not even use 12,375. You can still use 12,400 divided by lambda in Armstrong unit, and your answer would be in EV or electron volts. Remember the shortcut. Now again, if lambda of the radiation is greater than lambda naught, if it is greater than lambda naught, then no photoelectric effect, no matter what you do. That implies that lambda should be less than lambda naught. Simple things in this chapter. If you remember these simple things, you should be doing pretty nicely in this chapter. I'll give you 2 minutes to note it down. You note it down?
Yes, sir.
Everyone has noted it down, bacha?
Completed, sir.
Okay. Now what we got to do is study this photoelectric effect. So we have this heading which is known as experimental study or arrangement. Experimental arrangement for studying PE. You understand the meaning of PE? Photoelectric effect. Now, your books, you might see some very fancy diagrams for this. I'm not for fancy stuff. I just give you the simplest possible diagram, which just makes the point clear that what is going to happen here. So I'll just give you the simplest possible diagram and I'll try to make sense out of that diagram rather than giving you a diagram which probably does not make any sense. So this is the diagram that I will use, and it's a very simple diagram. You can see I'm a simple man from a small town, so I use simple things. Now remember, now wherever you see those fancy diagrams, and one of them is I think in your module. Do you have the module with you? Have you had the module with you? That book?
Yes, sir.
Yes. So you can see that diagram. I think you will have this diagram in your module. I'll show it to you. So don't worry. Both are same actually. They are not looking same, but they are actually both same. The one in the module is a more sophisticated version, trying to make the same point in a sophisticated way. So I think this is the diagram from your module, if I'm not wrong. This one is a diagram from your module, yes or no? This one is a diagram from your module, yes?
Yes, sir.
Okay, this is just a sophisticated version of the same thing. They have put a rheostat and all those stuff. That rheostat and all those stuff is just to vary the current in the circuit, so the voltage and the current could be varied. Nothing that makes this one more promising than the one I had drawn. The one that I have drawn is just a simplified version. The one that they have drawn is a version where you can change the voltage and you can change the current in the circuit. So don't worry about it. You can just understand it without having this sophisticated diagram. So you can just draw a simpler version of the diagram, which I think I have drawn here. The only thing we have to understand here is this battery ka voltage I can change by some means, and I will see what effect does it have on other things. Okay, so I will need to have some arrangement to change the potential difference of this battery. For that, they have kept this rheostat, nothing else. So I'll give you a minute to draw this diagram. It's a simple diagram. It's not very complicated. It's just a simple thing. Experimental study of photoelectric effect. Have you noted down this diagram, bacha?
Sir, 1 minute.
Sir, 2 minutes.
Take. See, this diagram is the entire chapter, beta. To understand this diagram, everything is done. Nothing else. And we'll do one thing aram se, coolly. Long breath we'll take and then we'll do it coolly. Simple steps. Note it down carefully.
Done, sir.
Everyone,
1 minute, sir.
should I wait more? Shall I go ahead? Shall I go ahead, bacha?
Yes, sir. Completed.
Okay. Now remember, when we are doing the experimental study of this, we have some means of changing the potential difference of this battery. Now, first thing first, let us first see what are things here. What is this P? This P is the metal. This surface where this things are falling. This is the metal surface. We call it photosensitive metal. This photosensitive, when light falls, it does something. Now this is normally kept negative with respect to this one, So this point is positive and this point is negative. Do you understand this? Looking
Yes,
at the connections of the battery.
Yes, sir.
So the positive side becomes your anode. So this gentleman is your anode. So you can just note it down. This is your anode. Normally this is your anode and your metal plate is your cathode. No doubts on this one? Yes or no?
Yes, sir.
Photosensitive metal. Now let us first see what happens if we just vary. We will vary one thing. We'll just vary the potential difference V. So the first heading that we are going to write is variation of photoelectric current with V. You understand V? V is the potential difference between the cathode and the anode. So heading A, variation of PE. PE means photoelectric. I means current. PEI, photoelectric current with V. You understand the meaning of V? V is the potential difference between what? The cathode and the anode. So we'll just write what are the observations that are made. What are the observations are made? Now, if I keep point Q at zero potential with respect to point P, I mean, I don't connect any battery, a very small current flows through the circuit. If the plate Q is at zero potential with respect to plate P, a very small current flows in the circuit because of some electrons of very high kinetic energy reaching the plate Q. But this current has no practical unity. But this current exists because of very high kinetic energy of some of the electrons that are emitted. Do we understand this?
yes, sir.
I've kept it
Sir?
as zero potential. Zero potential means they are at the same potential. Even if they are at the same potential, some current flows, some electrons are emitted. Great point. So some electrons are emitted with some kinetic energy, even if there is no potential. You understand this first point?
Yes, sir.
Yes, sir.
Now, what will happen if I increase the potential? If I increase the positive potential, we find that the current increases. We find that the current increases as more and more electrons are now able to reach the other side. So as the current is increased, if as the potential is increased, as the anode is made more and more positive, as the anode is made more and more positive, current increases because more electrons which had lesser energy are now able to reach the plate Q. That means from these two statements, we can find out that electrons which are emitted, wrong color, electrons which are emitted are of different kinetic energies. Do we understand this?
Yes, sir.
This is the second observation. Now, if I keep on increasing this potential, do you think that the current will keep on increasing till infinity? Will that happen? Will the current keep on increasing always? Or there will be a time when something happens? So if I keep on increasing this positive potential, current increases, but after some value, the current does not increase any further, because at this point, all the electrons which are emitted from the plate have already reached the plate Q. This current is known as saturation current. So if I keep the plate at the same potential, some electrons reach. If I increase the potential, more electrons reach. But if I keep on increasing the potential, at one point, the current becomes constant. That current is known as the saturation current. Do we understand this?
Yes, sir.
Yes or no? So we will go ahead and see what happens if you do the reverse of it. If you make anode negative with respect to the cathode, so anode becomes cathode and cathode becomes anode, then what happens? So we will see that in the next class. I hope you have understood till this point. Yes or no, everyone?
Yes, sir.
Note this point.
sir.
Each and every point beta is a question that is going to come in your exam. Take that in writing. So I'll see you in the next class. I hope you have noted this down.
Sir, no, sir.
So I'll keep the screen sharing on. Don't worry. I'll see you in the next class. And I think that the next class, probably we will be able to finish this. So we have taken some steps forward in today's class. Probably for you, I will be able to finish it in the next class. So good luck. God bless all of you. Any doubt? I'm always there. I'm omnipotent and omnipresent. I'm always present. So just send your doubt and I'll clear it. Take care. Have a nice day, bacha. God bless you all.